Welcome to Young Talk Initial Sensor. If a drone loses its GNSS signal, what does it rely on to keep flying? There is only one answer, the IMU, but the real issue is this. In satellite-denied environments, the failure of the vast majority of drones is not due to problems with the motors or flight controller, but rather a total navigation breakdown caused by uncontrolled IMU drift. During high-altitude, long-endurance missions, a tiny bias error can escalate into a positioning deviation of hundreds of meters within just a few minutes. So, today, we will clarify three things. How exactly do you choose an IMU for high-end drones? Which parameters in the datasheet are the truly critical indicators? How does factory calibration determine actual performance? High-end drones typically operate in three types of extreme environments. First, prolonged GNSS-denied conditions, potentially involving continuous flight for hours or even over 10 hours, where positioning relies solely on inertial navigation. Second, high dynamic maneuvers with angular velocities reaching hundreds of degrees per second and accelerations exceeding 5G. Third, extreme environmental conditions, ranging from high ground temperatures to lows of 50 degrees. Add to this the effects of intense vibration and electromagnetic interference. Consequently, consumer-grade IMUs are completely inadequate. Tactical-grade MEMS or fiber optic IMUs must be used. The core of model selection, it goes beyond simple specification sheets. What truly matters is not merely a few basic parameters, but 5 in-depth indicators. First, vibration sensitivity, G sensitivity, directly introduces drift in high vibration environments. Second, regarding the coning effect and coning errors, high frequency compensation must be supported, generally 1 cars. Third, a mismatch between positive and negative scale factors leads to systematic drift. Fourth, installation errors and repeatability issues exceeding 0.05 degrees significantly amplify errors. Fifth, the output rate is synchronized with time. The rate should be at least 400 Hz, ideally 1000 Hz, and the PPS synchronization error must be less than 50 microseconds. Factory-level calibration is the true source of IMU performance. It's not just measured, but established through calibration. Accelerometer calibration uses the 12-position flip method to model bias, scale factor, and axis misalignment. Gyroscope calibration utilizes a multi-rate turntable to perform tests ranging from +10 to +400 degrees, enabling the determination of non-linearity and cross-axis errors. G-sensitivity calibration establishes a 3x3 compensation matrix through 10G centrifuge or vibration testing. Full temperature calibration must cover the range from 50 deg to +185 degrees C and account for temperature hysteresis effects. Ultimate goal, full temperature bias error of less than 0.01 degree H. On-site calibration and pre-flight alignment. Stationary base alignment establishes the initial attitude using gravity in the Earth's rotation. Dual position alignment involves a 180-degree rotation followed by a second measurement capable of improving heading accuracy to 0.01 degree. Level, GNSS-aided alignment, completing the attitude initialization while the system is in motion. Zero velocity update ZOPT utilizes a stationary state to infer and correct the bias in the system. Online filtering, continuously correcting errors during flight using GNSS and the barometer. Engineering reality, proper installation matters more than a high purchase price. The vibration damping design can achieve a reduction of more than 20 dB. High frequency vibration. The lever arm between the IMU and the GNSS antenna must be measured precisely, with errors kept within the millimeter range. High-end systems typically employ a fiber optic IMU as the primary system and a MEMS IMU as a backup to achieve redundancy and fault tolerance. Summary: the performance of high-end drone IMUs does not depend on a single parameter, but rather on calibration standards, temperature stability, and system-level engineering design. Because in real-world missions, the IMU is not merely a sensor, it is the nervous system of the drone.